Global manufacturers record $1.4 trillion in annual losses. Those losses rarely stem from poor product design or weak market strategy. They result almost entirely from unplanned machine stoppages. For a typical large enterprise plant, a halted assembly line drains roughly $5,600 of revenue every single minute it sits idle. Traditional systems fail because they cannot self-correct when reality deviates from the schedule. If a belt stops, no automated alert triggers. The line stays dead until an operator physically spots the halt, manually raises a ticket, and updates a spreadsheet. This delay creates what plant managers call the capacity gap, a persistent 12 to 18% variance between what the scheduling software predicts and what the physical floor actually produces. Latency in discovery, the gap between a mechanical halt and human awareness, represents the primary bottleneck in modern industrial production. Reducing latency requires a transition to the software-defined factory, where artificial intelligence acts as a living system, proactively monitoring the entire operation. This architecture utilizes a decoupled multi-agent operating system, distributing factory intelligence across specialized agents that handle discrete tasks like scheduling, capacity planning, and maintenance. Implementing autonomous AI agents into physical manufacturing environments introduces significant engineering tension. Replacing rigid, programmable logic with large language models carries the serious risk of cascading hallucinations or erratic robotic movements. True autonomous manufacturing relies on strict deterministic boundaries. The system must contain the AI's logic rather than simply deploying a smarter, unconstrained algorithm. This system schematic outlines the foundational rule of the architecture: prohibited direct communication. The specialized agents are never allowed to talk directly to one another. All data must pass through the central BigQuery master ledger. This ledger acts as a single source of truth, compiling all enterprise operational data into one chronological, immutable audit trail. Every decision and event is recorded permanently. To move data in and out of the ledger, the architecture uses Google Cloud PubSub message queues instead of direct API connections between the agents. By forcing all interactions through this centralized asynchronous ledger, the system prevents cascading errors. If one agent fails or hallucinates, the isolation prevents it from triggering a chain reaction across the factory floor. At the top layer, the Production Schedule Optimizer (PSO) and Capacity Planning Agent work in tandem. A new order enters BigQuery as waiting. The PSO wakes every 30 seconds, checks the ledger, and uses the LLM to compute an optimized schedule. The system enforces a strict cost control mechanism here. The LLM is only invoked if the ledger flags a rush order or if the schedule requires a complex shift. If there are no changes, the AI stays dormant, driving idle cloud compute costs to zero. Simultaneously, the capacity planning agent reads the same ledger to monitor belt utilization, ensuring the PSO doesn't route too many jobs to a single production line and cause a bottleneck. Efficient agent design uses simple, deterministic polling loops to trigger the LLM, preserving expensive compute exclusively for complex orchestration tasks that actually require it. Physical operations require immediate reflexes. A heavy unit shifting out of alignment on a moving belt cannot wait 30 seconds for a scheduled pull. The shop floor control agent executes micro-corrections under 12 seconds. It bypasses the LLM, using deterministic scripts to evaluate rotation. The LLM then calculates the corrective angle, issuing commands via a selective ACK protocol to ensure no robotic action is lost to network failures. This architecture allows the agent to issue precise, direct commands to hardware, demonstrated here operating a Franka robotic arm inside an NVIDIA Isaac Sim digital twin, which enforces real-world physics and gravity. Physical safety demands that heuristic AI decision-making remains encased entirely within rigid, mathematically deterministic pretexts. How is a repair ordered without direct agent communication? This diagram shows the asynchronous handoff. The shop floor agent logs a stop status into BigQuery and shuts down. The isolated maintenance agent pulls that database every 30 seconds, reading the stop status as its trigger. The maintenance agent immediately dispatches a robotic repair command to the physical floor. Simultaneously, it applies a hard-coded mathematical rule to the ledger, automatically shifting all downstream job delivery times back by 45 minutes to account for the belt repair. This complete sequence, detection, logging, dispatch, and global schedule recalibration, executes in approximately 1 minute. In a traditional factory, the manual ticketing process takes 45 minutes before a technician is even alerted. This transition from manual reporting to asynchronous agent pulling collapses the discovery timeline from nearly an hour down to 60 seconds. Operating at maximum efficiency is dangerous if the system only understands mechanical physics. To scale safely, the architecture must transition into a living factory, one that continuously monitors human psychology and worker capacity alongside the hardware. Vision-based AI models, analyzing feeds from overhead cameras, track the human operators. They monitor compliance with safety protocols and calculate real-time physiological metrics to detect early signs of worker fatigue. If the camera agents detect exhaustion, they write that data to the ledger. The production scheduling agents read the human capacity limit and autonomously throttle down the speed of the conveyor belts, slowing the work to match the operator's physical state. This establishes the foundational governance rule of the operating system. Worker safety is the primary, hard-coded directive. It is programmed to explicitly override all downstream productivity, scheduling, and quality metrics. An optimal autonomous system does not treat humans as fragile mechanical bottlenecks. It optimizes for their physical well-being as a strict mathematical requirement for long-term operational scale. As detailed in this matrix, expanding this architecture to manage highly complex multi-line facilities requires upgrading the agent capabilities. The most critical upgrade is the shift toward proactive predictive maintenance. The maintenance agent will move beyond rule-based triggers and deploy machine learning to analyze time series sensor data, calculating probabilities and repairing assets weeks before a physical breakdown actually occurs. This automation strategy directly targets the 12 to 18% capacity gap, replacing reactive firefighting with a system of continuous, sub-14-second microcorrections. Managing a factory in this environment shifts the human role away from manual monitoring. The core competency for a plant manager becomes prompt engineering, algorithmic governance, and designing the strict parameters that keep the AI within safe bounds. The software-defined factory model shifts the human operator into the role of a strategic orchestrator, tasked with overseeing the intelligent systems that now manage the minute-by-minute flow of production.